If you want the perfect immersive sound setup, audiophiles say you need a speaker positioned in every corner of your room, while modern tech companies say a single soundbar sitting underneath your TV can do the exact same thing using something called spatial audio. Now, to see if this is real acoustics or just a marketing gimmick, I built acoustic scale models of both a surround sound setup and a soundbar setup. Then I scanned both inside my CAT scanner rig to see how the invisible sound waves are moving and interacting in real time. This should give us a perfect visual of the limitations of each setup, and to show how both systems are actively trying to hijack your survival reflexes to make it feel like you're about to become a tasty snack for some kind of monster. Now, to map out sound waves in an area, audio engineers typically use microphones to measure the sound waves at multiple points. They have to move the mic to lots of different locations around the room, which allows them to plot out the sound field. Now, to me that sounds like a total pain in the arse. I just want to take a video of the area and magically see the sound. And this is where the CAT scanner comes in. By using strobe lit Schlieren imaging, we can see actual sound waves in real time. But we can also take a step further with the CAT scanner. We can rotate the test area and take Schlieren images from every angle. Then we can stitch the images together to create a full 3D map of the sound field. And no more moving microphones. Now, you may be thinking to yourself, how are you going to see a 3-foot long sound wave using an 8-inch mirror? It's just not going to fit. And this is where the magic of acoustic scaling comes in. To really get an idea of what's happening, we're going to need a guinea pig. Now, if we compare the distance between this guinea pig's ear and my own ear spacing, they scale at almost exactly 4:1. So we can take the Schlieren test area with guinea pig and scale it up to human size. The ultrasonic 40 kHz sound waves become 10 kHz, which sound like this. Then the 20 kHz waves scale to 5 kHz, which sound like this. So now I can use one of those small 40 kHz range transducers and scale it 4:1, simulating a 10 kHz sound wave. This scales the test area to roughly 3 foot. To get lower frequencies, I bought a bunch of cat repellent speakers. AliExpress must think I'm completely infested with cats. These speakers operate about 10 to 20 kHz, which scales down perfectly to 2.5 to 5 kHz range, which is ideal for directional sound because most of our sense of sound's direction comes from higher frequencies anyway. Now, to see the sound waves, I could have just used a CAT scanner I built in my last video, but I wanted to steer the sound waves. This means I need to delay the audio signals relative to each other, so I needed to build an 8-channel audio signal generator. I took the opportunity to improve 1 or 2 small things. It'll only take a couple of minutes, or so I thought. Number 1 was jitter. My old CAT scanner rig had a lot of timing jitter, which made the images look a bit fuzzy. And I knew I could do better, so I moved all the low-level timing onto this Pico board. It was so cheap I couldn't resist. This allowed me to dedicate an entire processor just to the timing, and the jitter was completely gone. Next up, I added the 8 audio channels to the Pico. My old CAT had only 1. This way I can drive 8 speakers, exactly like a 7.1 surround sound setup. This lets me adjust the frequency and delay on each individual speaker and have them all perfectly synced to the LED strobe, the camera and the motor. I added some small filters to convert the digital PWM signal into smooth analog waves. And while I was at it, I figured I may as well just add Bluetooth to get rid of all the long cables in my workshop. Now the main Pi just needs to send simple Bluetooth commands and the Pico generates all the complex timing and audio signals. So it should be easy to upgrade to any other kind of Pi in the future. But to actually drive the speakers, I need to boost the audio signals from the Pico across all the 8 channels up to about 24 volts. Now I could have just used 8 off-the-shelf amplifiers, but I thought it'd be much more compact to build my own custom 8-channel amp. And off down another rabbit's hole I went. I bought a bunch of these really temptingly cheap LM1875 amplifiers in a bag of 10, and I built up 2 custom PCBs. To save some soldering time, I left out a few of the recommended components from the datasheet, only to figure out they were a lot more than just recommended. And after a quick bit of backtracking and soldering, everything was finally working well. But then I was tempted by this lovely little cable reel, especially for YouTube. It looked so cute, but found the wires were so fragile that barely moving them made them snap, so I ended up replacing all the wires, which made me pretty sad. Then I found a cheap strip board peeled up when I tried to rework it, which made me even more sad. But I managed to bodge some wire links and all was good in the end. So if you're following along with building this yourself, All I would say is this: buy some decent wire and strip board. It's just not worth getting the cheap stuff. Also, screw it all down. There are way too many wires to get tangled up in, and stray metal on the workbench is not your friend. Not saying that I managed to pull the entire test rig down on top of myself or anything. Now, with all the electronics soldered and bolted down, I hooked up all the speakers for the surround sound setup. I 3D printed this ring with interchangeable mounts so I could quickly swap between the 40 kHz rangefinder and the cat repellent speakers. Then I 3D printed a nice bucket seat throne for Mr. Fuzzy Face Friend. And he was good to be a guinea pig. Now a bit of a reality check that the test area scales down to roughly 3 foot, so this is definitely going to be immersive. But the wave mechanics will still look the same as an actual surround sound setup. Now if I start with a basic stereo setup, you can clearly see 2 waves as they hit his head. But what the images don't show are the psychoacoustic effects of those waves. Mr. Guinea Pig will perceive the sound as coming from the exact middle of the 2 speakers, a phantom center, so long as they hit his ears at the exact same time. If one side is delayed even slightly, his brain will subconsciously assign the sound's direction to the very first wave that hits his ears. Now the exact same thing happens in a surround sound setup, except this time if he's sitting in the perfect sweet spot where all the 8 waves arrive at the exact same time and volume, the sound will appear like it's originating from inside his own little fuzzy head. This is a bit of an unnatural feeling and will subconsciously make him want to move his head just to try and localize the sound. And if you look at the sound waves closely, you'll see that they flow around Mr. Guinea Pig's shoulders. The physical interaction colours the audio, meaning it would actually sound slightly different to him from different angles. Both animals and humans have evolved to subconsciously react to specific sound waves. Out in the wild, localizing sounds instantly is the difference between catching a tasty lunch and becoming a tasty lunch. Movie sound designers hijack these exact same survival reflexes to make you jump out of your seat in a movie theatre. But no guinea pig has their own surround sound setup. They all use soundbars, of course. Soundbars attempt to replicate a sound field using 2 main techniques. The first is HRTF, or Head Related Transfer Function, not to be confused with HRT. HRTF tries to mimic how sound flows and changes when it physically hits your body and ears, like you've seen with Mr. Guinea Pig in the surround sound setup. The software colours the audio by adding harmonics and delays to make the sound look more natural when it enters your hole in your ear. Now the second technique is beam steering, and beam steering looks straightforward in the textbooks. You just need to delay one audio channel relative to the other to steer a beam of audio around your room, easy peasy. So I built a quick prototype to bring all my raw academic knowledge into the real world. This was 100% accurate, of course, about 1% of the time. It was total rubbish, in other words. For version 2 I used Waveguides to reduce the speaker dimensions. This let me space the sound slots at an ideal of half a wavelength, which is roughly 4.5mm at 40 kHz. It was slightly better, but the sound kept on bouncing off the inside of the waveguides as they were just too shallow. Now we don't talk about version 3. For version 4 and 5 I tried to beam steer in the x-axis only, using a staggered arrangement. Still not much luck there. By version 6 I started to realise just how difficult it would be to take this from theory into the real world. Much like those fancy cookery books, I felt utterly deceived by the pretty textbook diagrams that made this look so effortless. I would have had more success steering beams from my own arse. I made the waveguides longer and smoother, which was better, but it's as if the speaker parameters change even slightly with time or temperature or frequency. It's so incredibly hard to keep the acoustic phases all aligned in code. I certainly wouldn't want to be putting my stamp of approval on it. So instead, high-end soundbar manufacturers often just point the speakers at the ceiling or walls. Much easier. The rays intentionally fire an acoustic beam past you, bouncing it off the wall or ceiling so that it hits your ear from the side. Your brain locks into the first wave, which tricks you into thinking that the speaker is sitting right over there. But we run into a major problem: soft furnishings. This relies on clean, reflective walls. But what happens if Mrs. Guinea Pig purchases a fancy new pair of curtains? Well, soft materials kill the reflected sound waves and the immersive sound, so the sound never reaches poor Mr. Guinea Pig's ears, and his curtains on his 3D sound illusion. So traditional surround sound setups win, right? Well, not exactly, because surround sound kind of sucks too. Nobody lives in a perfect circle and there's way too many cables. Just moving to a different spot on the couch totally changes the sound you hear, especially when you add in random wall reflections and ceiling reflections. So you have to constantly calibrate for your exact location. And what about poor Mrs. Guinea Pig sitting at the other end of the sofa? No wonder she's not impressed by the sound of the helicopter swooping in. Honestly, it's all a bit too much hassle for me. I'm just going to stick with headphones. What can go wrong there? That'll do, pig. Guinea pig, I mean. To a microphone or to my Schlieren camera, these are all just fancy waves. They're a bit clinical, 2D waves of air pressure moving across your screen. But human hearing is so much more than just capturing raw data. Our brains take these invisible waves of pressure and translate them into thoughts and emotions. Scary word, I know. One sound pattern can make you happy, while another slightly misaligned shape makes you jump right out of your seat. Now, tech companies aren't just vibrating speaker cones, they're actively playing with your nervous system like a set of bagpipes. Now, to keep these bills going and to fund future more advanced projects, I'm launching a Patreon. If you like this kind of engineering deep dive, please consider supporting the channel via the links in the descriptions below. And if you want to replicate anything you see in this video, or maybe even try and steer beams of sound from your own arse, I've included all the CAD and the code in the GitHub links down below. Now, thanks for watching, have fun, and I'll see you next time.